Hello and welcome to our today's video on dimensional reduction. Here we will be unlocking insights from higher dimensional data. Higher dimensional data sets can be overwhelming, but dimensional reduction techniques like principal component analysis (PCA) help simplify them. In this video, we will be exploring multicollinearity, the importance of dimensional reduction, and how to apply PCA in Python to make your data more manageable and interpretable. Let's dive in. First, we will be covering understanding multicolority. Before we jump into dimensional reduction, let's us understand a key challenge in high dimensional data called multicolority. Multicolority is a high correlated variable. Multicolority occurs when two or more predictor values variables in a regression model are highly correlated. This means that the variables share similar information, making it hard to access their individual impact on the outcome variable. Visual showing inflated regression coefficient estimate. One of the main constraints of multicolority is implemented variance in the regression coefficient. This leads to unstable estimates, meaning small changes in the data can cause large inflammation in coefficient values. As a result, your model might be unreliable. Interpretation can also become a tricky as the coefficient no longer reflect the true relationship of each variable with the outcome. This can lead to misleading conclusions and misinterpretation of result. Detecting multicolority. Now let us look how we can detect multicolority using Python. Colorative coloration matrix. One way to detect multicolority is by using a correlation matrix. A correlation matrix shows the relationship between variables. If two variables have a related relation close to 1 or -1, they might be higher collinear. Variance inflammation factor (VIF). Another method is calculate. Another method is calculate for calculating is the variable inflammation factor (VIF). VIF quantifies how much the variance of a regression coefficient is implemented due to polarity. A VI value over 5 or 10 suggests a potential problem. Equivalent values and conditional numbers. Lastly, we can use equivalent values and conditional numbers of collection correlation matrix to assess multicollinearity. Large equivalent values or a high condition numbers indicates potential issues. Next in we have importance of dimensional reduction. So what is dimensional reduction so important? Improved model performance. By reduction dimensionality, we can improve our model performance, removing redundancy, information, and noise, help build more accurate predictive models. Enhance interpretation. Dimension reduction also enhances the interpretability of complex data, making it easier to understand and relationship between variables and identify key drivers for the responses. Reduce computational cost. Moreover, reducing the number of variables decreasing the computational cost, making model training and inference more effectively. Improved visualization. Finally, dimension reduction enables better visualization of dimensional data. By projecting the data into lower dimensions, we can discover patterns that could be different to spot otherwise. Next in we have introduction to PC principal component analysis. One of the most powerful technique for dimensional reduction is PCA component analysis. PC linear transformation. PC works by applying a linear transformation to identify the principal components which are ortho- orthogonal, directional, that captures the maximum variance in the data. Variance maximization. The principal components are ranked based on the amount of variance they explain, with the first component capturing the most variance, the second the next most, and so on. Dimensionality reduction. By selecting a subset of principal component, we can reduce dimensionality of the data while retaining most of its valuable information. Next, we have preparation of data for PC in Python. Now let's now see how we can apply PC using Python. But first we need to prepare the data. Step 1. Import libraries. Start by importing the necessary libraries like NumPy, Pandas, and skitlearn, uh, scikit-learn. Step 2. Load and pre-process data. Next, load your data into a Panda data frame. Ensure your data is numerical and handle any missing values. Step 3. Feature scaling. PC is sensitive to scale of features. So it is important to scale the features so that all features have a same magnitude using techniques like standardization to scale your features. Next in we have implementation PC abstraction components. Let us now apply PCA to reduce the dimension of our data. Step 1. Initialize PC. First, we initialize PCA and specify how many components we want to retain or the amount of variance to explain. Step 2. Fit and transform data. Next, we fit the PCA model to the scalar data and transform it into the principal compound space. Next in we have determining the optimal number of principal components. How we can decide how many principal components to keep? There are few strategies. Strip plot. A strip plot shows the eigenvalues of each principal component. The elbow in the plot where the eigenvalues start to level off indicates the optimal number of components. Explain variance. And another method is to look at the commutative explain variance, which tells how much of the total variance is captured by a given number of components. Aim for a high proportion like 80 to 90%. There always a trade-off. Too few components can lead to information loss, while too many might not offer significant dimensionality reduction. Next in we have visualization and interpretation PCA results. Once you have reduced the dimensionality, you can visualize your data in lower dimension space. This provides new insights into the relationship between variables. You can also interpret the PCA loading, which all shows how much which shows how much each original features contributes to each principal components. This helps us in understanding the meaning behind each component. Next in we are applying PC for our projects. By applying PC, you can overcome the challenges of high dimensionality, improve model performance, enhance interpretability, and reduce computational cost. It's a powerful technique for unlocking insights for complex data sets and making data analysis more effective. That's a wrap up on dimensional reduction and PC. I hope you found this video helpful in understanding how to reduce dimension and improve your data analysis. Thank you for watching, and I will be seeing you in the next video.